We know that a sequence is a list of numbers in a certain order, and we've been working with explicit formulas for sequences. So if I have a sequence described as a sub n, I might think of it having like a first term, a second term, a third term, and so on. So a series is the sum of the terms in a sequence. So a series is the sum of the terms. A series is going to give us a value because we're going to add up all of our numbers from our sequence, all of our terms from our sequence. So I could see that if I have a series of some sequence a sub n, that I'm just adding my first term, my second term, my third term, and so on. So we need to get comfortable with the notation for how we write a series. We're going to see the Greek letter sigma. This is capital sigma, uppercase sigma. We sometimes think of that as the summation, and that tells us that we are summing or adding the thing that follows. We have a lower limit, so this index n equals 1, this is telling us to start at 1. So we're going to start at our first term from our series a sub n, and we have an upper limit, which is 4. And notice sometimes our upper limit is a value, sometimes it's infinity, which means we never stop adding. And this is going to tell me to add all of my terms from 1 to 4 of this sequence, like add up the terms of this sequence. So I could read this as the sum of a sub n as n goes from 1 to 4. In other words, this is the sum of all of the terms of some sequence defined as a sub n from the first term to the fourth term. So from when n equals 1 to when n equals 4. So when we see a series where we have a value on top, so when our upper limit, in other words, is a number, so when k is a number, this tells us to start adding, in this case, start adding with our first term, because we would start when n equals 1, and stop when n equals k. So that's going to give us a finite number of terms from our sequence to add up, and we call this the kth partial sum of the series. So that depends on what the number k is. Like up here, we would think of this as the fourth partial sum because we are starting at 1 and adding up to 4. So if k is 2, we'd think of that as the second partial sum. However, when we add up all of the terms of a sequence and we don't have an upper limit, so we are adding literally all the terms forever and ever, this is what we call an infinite series. And we might see this written two different ways. We could see this where our summation has an upper limit of infinity, or we could also write this as the limit as k approaches infinity, and then the rest of this looks like our kth partial sum. So from when n equals 1 to when n equals k of a sub n, we're adding up all of those terms from our sequence. All right, so for these first few examples, we just want to get comfortable with this notation. And so in the first example, we are asked to evaluate the series, or rather, really the fifth partial sum of the series, I should say. So we're evaluating this for n squared, and we're going to start at 1 and stop at 5. So when I go to write out my terms, I'm going to start with my first term. Well, my first term is just when n equals 1, so that's 1 squared. My second term is when n equals 2, so that's 2 squared. And I'm going to keep doing this until I get to 5 squared, our fifth term. So when I add this up, this is really just 1 plus 4 plus 9 plus 16 plus 25. And when I add all those numbers up, I get 55. So again, a series gives us a value, and the value of this series is 55. All right, in the next example, I might notice that my lower limit or my index is 0. So we're beginning at 0. We said in a sequence, we always begin at our first term, but in a series, we could actually start wherever we're told to start. So we're going to start where n equals 0. We're going to stop where n equals 4. Oops, sorry, that's a 2, not a 3 there. Oh my goodness. All right, that 3 really didn't want to erase. And so if I write out my first several terms, I'm going to start with 3 times 2 to the power of 0 plus 1. So again, that's going to be where n is equal to 0. I'm going to add to that my next term, my first, or when n equals 1 rather. So 3 times 2 to the power of 1 plus 1. I'm going to add to that 3 times 2 to the power of 2 plus 1. And I'm going to keep going until I substitute 4 for n. All right, so we've got n equals 0, n equals 1, n equals 2, n equals 3, n equals 4. So when I go to add this all up, I know this is initially like 3 times 2 to the first power, which is just 6. We're adding to that 3 times 2 to the second power. Well, that's 3 times 4, which is just 12. We're adding to that 3 times 2 to the third power, which is just 3 times 8, which is 24. And what we might notice is that as we're adding, the terms of our sequence are doubling because this is a geometric sequence. So it might be faster to realize my fourth term is just going to be 48, and my fifth term is just going to be 96. All right, so when we add those up, 6 plus 12 plus 24 plus 48 plus 96, we get 186. All right, for this last example, you may want to pause the video, try this one on your own, and check it afterwards. Notice that we are starting where n is equal to 5. So when I calculate my sum, I'm going to start by plugging in a 5. So I've got negative 1 to the 5th power divided by 5 minus 2. I'm going to add to that negative 1 to the 6th power divided by 6 minus 2. Oops. We'll add to that negative 1 to the 7th power divided by 7 minus 2. And negative 1 to the 8th power divided by 8 minus 2. So I know when my exponent is odd, that negative 1 is still negative. 5 minus 2 is 3. So my first term is really just negative 1/3. My second term is positive. I can see this is an alternating sequence. 6 minus 2 is 4. Then I have a negative 1 on top. 7 minus 2 is 5. And a positive 1 on top. 8 minus 2 is 6. So we're adding negative 1 plus positive 1/4 plus negative 1/5 plus 1/6. And to add those up, we need a common denominator. So I know the least common multiple of 5 and 6 is 30. 3 is also a factor of 30, but 30 is divisible by 2 and not 4. So if I double that, 60 is going to be the least common multiple of all 4 of those terms. So when we go to add this up, let's see, we have to multiply 3 times 20 to make 60. So we have a negative 20 on top. To make 4 into 60, I'm multiplying by 15. To make 5 into 60, I'm multiplying by 6. So I get a negative 6 on top. And no, I'm not. That was to make 30. Sorry, I'm multiplying by 12. So a negative 12 on top. And then finally, this last term I would multiply by 10 to get a denominator of 60. So when I add that up, negative 20 and negative 12 is negative 32. But we're adding to that a positive 25. So we are left with a negative 7/60. So negative 7/60 is our value there. All right, so the last thing we're going to try is to rewrite each of the following using the summation notation, meaning using that capital sigma to condense what we're adding. So in order to do this, this goes back to the idea that I need to be able to write the explicit formula for a sequence. So if I consider my first term, like n equals 1, my second term, n equals 2, n equals 3, n equals 4, I notice that my numerator is the same as just whatever n is. So my numerator is just n. I might also notice that my denominator is increasing by 2, and so my denominator is odd numbers, but we're not starting with the first odd number. So if I think of increasing by 2, I know that that's going to have to do with 2 times n. So to make a 3 from when n equals 1, that'd be 2 times 1 plus 1. To make a 5 from n equals 2, that would be 2 times 2 plus 1. So our denominator is 2n plus 1. So when I go to write this using the summation notation, I know that I want my index to be where I'm starting, so n equals 1. And I could see that the sum stops at the 9th term. So we're adding all the way up to where n is equal to 9. And then our sequence that we're summing is n over 2n plus 1. So that is how we would write this using the summation notation. All right, for the last example, we could see that we have another sequence where the signs are alternating. And a couple things stand out to me. One is that I see this dot, dot, dot here. And this helps me know that this is going to be an infinite series. So when I rewrite this with summation notation, I know my upper limit is infinity. The other thing is it helps me to think of that first term as having a denominator of 1. So I notice that my numerator is just always 1. We'll deal with the alternating part in a moment. My denominator, hopefully we're beginning to recognize this pattern, 1, 2, 6, 24, 120. This is n factorial. So again, this would be like 2 times 1. This would be 3 times 2 times 1, 4 times 3 times 2 times 1, and so on. So when we want to get our alternating sign, I know that I really need a negative 1 on top, and I need to think, is this to the power of n or n plus 1? So if I were to leave this to the power of n, when I plugged in 1 for my first term would be negative. I want my first term to be positive, so I'm going to make that n plus 1. All right, so now when we put this together, we're going to start at 1. We're going to add, well, forever. This is an infinite series. I have negative 1 to the power of n plus 1 over n factorial.